Well, guess what? I do know how to calculate the integral of square root of dt. And the answer is really surprising. So just bear with me, because it turns out this integral won't be a regular integral, but a stochastic integral, or what's called a random integral. And in this video, I will just tell the facts. If you want to see the proofs of it, just click on the links once I have them. So, here's a fact. So it turns out this is related to Brownian motion, which is really random motion. So the fact is, there exists a process, W, which depends on t, and whose output is what's called a random variable. And you have to think of what it is as follows. If you roll a die and something happens, then you have some output. If you roll a die again, you may have a different input. So there is something called a Brownian motion with the following property, such that at 0, no matter how you roll your dice, at the beginning you will have 0. So W0 equals to 0, except for like impossible events. So this is what's called almost surely. Surely, you must be joking, huh? And moreover, so let me draw a picture. So at time 0, the Brownian motion is 0, and every time you roll a die, it gives you a different value. So you have this, and at time t you get this value. It's possible that for some other time t you get some other value, depending on how drunkenly you walk starting at 0. But what we do know is no matter how randomly you go, first of all, you start at 0 almost always, and moreover, if you start at 0, it's very likely that you're still around 0 at the small time, and the way to write this is Wt minus Ws. Again, it's a random variable, and it's normally distributed. So N0t minus s, where t is greater or equal to s and greater or equal to 0. In other words, for example, if you start at Ws, so if you start at 0 and then you get Ws, and then you're at this point and you still start walking a little bit until t, well, it turns out Wt isn't that far away if t is very close to s. So it's normally distributed, and moreover, there's this memoryless property which says that, well, if you're here, then whatever you did in the past doesn't influence it. In other words, the increments, if you start here and then you go there and then you go there, all those increments are independent. So 3 Wt1, Wt2 minus Wt1, Wtn minus Wtn minus 1 are independent. Where again, T1 is positive, but it's less or equal to T2, which is less or equal to T3, less or equal to a Tn. Which should remind you of a Riemann sum, and in fact this is what we'll be talking about as well. So this, I'll take it as a given. The proof is a bit annoying, but if you want to see the proof, maybe I'll do it. I don't know, it depends on my mood. But the idea is sort of similar to the construction of the Riemann integral. You start with step functions, and then I'll be back. Okay, so if you want, the proof idea is you start with those staircase functions like that, hk, which again, those are called ha functions, like hair. And basically, the bigger k is, the smaller the interval and the bigger the height. And then you let sk to be the antiderivative of hk, I think starting from 0 up to a certain point. So the sk's, they would look like spikes like this. And then because you want this normally distributed thing, you just define your Brownian motion to be somehow the sum of ak sk of t, where ak is a normally distributed random variable. And it turns out once you have that, then you have actually the Brownian motion. But this is good. Let's take this as a given. How does that solve our problem with the integral of square root of dt? Here's the claim. I'm actually claiming that if you take w like this, and you take very small increments, dw, then it turns out this, because w is so random and so erratic, it turns out dw behaves like square root of dt. So claim dw equals to square root of dt in the following sense. Okay, so here's the fact. Maybe let me use the first whiteboard again. And again, I know there's a lot of setup, but once you define this, then we can play. And again, it does make sense. Just saying. So, fact. Okay, fact one if you want. So suppose you have an interval which is like positive, so it's contained from 0 to infinity, and let's define Riemann sums as before, or as in calculus. So fix n, and let ti just be a plus delta ti. And by the way, I'm presenting a simplified treatment. You could just let ti to be a random point in your interval as long as it's small. So AB, so the idea is this is T naught, T1, T2, up to Tn. Then, okay, well, we have those little discrete times, and suppose you take WTK and WTK minus 1. So TK plus 1. And you sort of consider the difference. So again, what it means is you start at A, and you do W of A, then you do W of T1, then W of T2, so baby steps. Okay, and the question is, what happens to the following? What happens when you take those little increments and you square them? Then, the sum from k from 0 to n of W, Tk plus 1, minus WTK squared. Okay, so, and the question is, what happens as n goes to infinity? Well, it turns out, again, because of our ansatz, that dw, it's square root of dt. Well, what this means is, somehow this is like dw squared. So dw squared should be dt. And remember, we know that the integral of dt from a to b is b minus a. And indeed, this is true. If you take the sum as n goes to infinity of this little Riemann sum, then you do get that it goes to b minus a. Possibly with some extra factors. So at least in the proof I've seen was 1 minus 0. But the question is, what kind of convergence? Because remember, this is not a function, it's a random variable. So if you take this sum, you have something random going on. So it turns out the convergence here is precisely in L2. In L2 of your random space. So remember, a random variable is just a function of randomness. And somehow what this says is, if you take this thing, you subtract b minus a, and you randomly integrate the square of it, you get a 0. So in the sense that, sense that if you take, again, the difference between the two, so k from 0 to n of w tk plus 1 minus w tk, again, squared, that's what we have. You subtract b minus a, and you square this, because it's an L2. Again, this is a random variable, so one way to integrate this with respect to randomness is to take the expectation. So what this means is if you take the expectations of this as n goes to infinity, you get 0. And this fact I will prove in a later video, so that's very interesting. And so how does that resolve our problem? So what is the integral from a to b of square root of dt? It's just the integral from a to b of dw, which is wb minus wa. So the integral of this weird sucker is actually a random variable. Namely, you start at 0, you do wa, and then wb, and somehow the distance between those 2 points is just, again, as random variables, is just this weird integral. So I think this is pretty cool. Who would have thought to introduce probability to solve this simple calculus problem? So Brown was apparently that smart. And in fact, you can do even more than that. So you can't just integrate square root of dt, but you can actually integrate any function times square root of dt. So in fact, it turns out if you take any function, and here very important, it's not a random variable, it's a deterministic function. It turns out then that you can integrate by parts. So think of just putting this d over here, and if you integrate by parts, you get gw from a to b minus integral from a to b of g prime w dt, which is just, g of b wb minus g of a wa minus integral from a to b g prime w dt. And to integrate this is just like doing Riemann sums. So you evaluate g prime and w prime at those little points ti, and you just take the limit of this sum. So this is actually, it's not that scary. It's really integrating with respect to w. And you're like, oh my god, this is exciting. Is this the end? Well, no, turns out there's more. So you can't just integrate square root of dt, you can also integrate w with respect to dw. And you get actually a very interesting answer. So the question is then, what is the integral of w dw? What is the integral from 0 to t w dw? It's weird, you're integrating a random variable with respect to that random variable, which is crazy, right? But intuitively, you would think that the answer is like 1/2 w squared at t minus w squared at 0. Well, this may or may not be the answer. So, in fact, this is really cool. So, suppose you have your interval, right? Let's say, again, you subdivided this, and again, from a to b or something, or from 0 to t. And you have tk and tk plus 1. And you let tau k be a very fixed number in this interval. So fact 2. So if tau k in this interval tk plus 1, it's defined by tau k equals 1 minus lambda tk plus lambda tk plus 1. And the point is, you always take the same lambda. And for example, for lambda equals 0, it's the left point. For lambda equals 1, it's the right point. For lambda equals 1/2 is the midpoint. So it's very important that this doesn't depend on k. So for some lambda. And suppose you take the Riemann sum. So let Rn be the sum from k from 0 to n of w tau k times w tk plus 1 minus w tk. This is really the analog of the integral of w dw. Because what does dw mean? It means you take small increments with respect to w, and you evaluate w at somehow a random point in that interval. Except the random point, it's like not that random, it's like uniformly random if you want. Then it turns out this Riemann sum converges to something really interesting. So as n goes to infinity, again, it's a random variable, so here the convergence is in L2. It converges to what you think it would, so wt squared over 2 plus a very interesting part, lambda minus 1/2 t. And this is very unusual because in Riemann integration, this integral shouldn't depend on where the point is, right? That's one of the chefs-d'oeuvre of Riemann integration. But it turns out for this kind of integration, that integral depends on which point you choose. So it's not quite well defined, and in fact, there are many different choices of lambda that are equally interesting. And there are two of them I would like to mention. Well, an obvious choice would just be, suppose, well, almost obvious. So what if you just choose the left endpoints? Which it makes sense in a second why I say that. So if you let lambda equal 0, then you have the most famous integral called the Ito integral. And in fact, the cool thing is there's an Ito Chen-Lu for that. And it's very useful if you want to study random differential equations. So the Ito integral, ITO hat, chooses lambda equals 0. And then in that case, so forgot to mention, of course, this thing by definition, as n goes to infinity, goes to that integral you want. Then we get that integral from 0 to t w dw. It's simply wt squared over 2 minus t over 2. And in general, if you want the integral from s to t or something, or from s to t, w dw is what you want it to be, so wt squared over 2 minus ws squared over 2 minus this annoying term t minus s over 2. By the way, remember that w0 equals 0, so it's, as I said, almost what you expect. Wt squared over 2 minus w0 squared over 2 minus t over 2. And I will prove that fact again in a separate video, but let me tell you why this is very good. First of all, it turns out it's a nice thing because there will be some very simple formulas for those integrals. So if you study stochastic stuff, then it turns out the Ito one is the best one because it's the one that gives you simple formulas. And moreover, I think this makes sense because what does lambda equals 0 mean? It means you always choose the left endpoint. And that's good because remember, it's a random process. So you usually don't know what the future holds. So by choosing lambda equals 0, you say, oh, I'm very cautious. I'm not going to bet because the future might be might be weird. So I'm just going to choose the left endpoints, because if I chose the right endpoints, it means somehow I could predict the future, and that's bad. Especially think in finance, right? Finance, choosing the left endpoints means you just choose the safest bet. And also, the reason we choose the left endpoints, because we don't know the future, and it turns out because of this fact, our process, our integral, will be a martingale. So remember, this is a random variable, and it turns out there's something called a martingale, which basically tells us that it's invariant under whatever the future is. So it's just what I talked about the future. And on the other hand, of course, what if you don't like this extra term? Well, you could just choose the midpoint, lambda equals 1/2, and then you get exactly the formula that we want. And that's what's called a Stratonovich integral. Which integral? And that's for lambda equals 1/2, and it's written as this, integral from 0 to t, w dot, so circle dw, and in that case you would have wt squared over 2. And similar here, you would have wt squared over 2 minus ws squared over 2. And this is great also because it turns out the regular Chen-Lu also holds. So if you do U sub, you can simply do U sub. Whereas for the Ito, you need a Ito Chen-Lu. That's slightly more complicated. But again, it's not a martingale. It's slightly risky because you say, well, you choose a midpoint, so you kind of know half the future. And lastly, what I want to say is, we define the integral of w dw, and it turns out we can now define the integral of any random variable with respect to dw. And it's just the same thing as a Lebesgue integral, because basically what made this work, this integral of w dw, is we choose w of a random point times the increments. Well, the only difference is for the for the general stochastic integral, instead of doing w, you just replace it by your stochastic process. So the integral from 0 to t of g dw would just be the sum from k from 0 to infinity, k from 0 to n, and you take the limit as that, of w tk plus 1 minus w tk. And instead of doing w, you do g, almost like g of tau k, but the idea though, okay, here I simplified a bit, but what you do, you first assume g is a step process, which means it's like constant on small intervals and with values gk. So technically you would do gk instead of g of tau k. And then all you would do, you would just take a general stochastic process, a general random process, and just approximate it by those step processes. And then you take a limit of those step processes over there. Just like for the Lebesgue integral, you generalize this from the Riemann integral by first taking the integral of step functions, and then you take the limits of everything. Alright, so I hope you like this excursion into this freaky integral of square root of dt. And again, if you want to see proofs of this, I will post them once I've made them. And if you want to see more freaky calculus like that, please make sure to subscribe to my channel. Thank you very much.